We are live.
Yeah, it's good.
It's
Start streaming and let's go already, okay?
does it have the microphone? Yeah, sure.
Traffic is not coming or is the
He's coming. I think he said that he's gonna wait. Okay.
So you're recording?
I'm recording.
Okay.
Or I'm not recording and this work of art will be lost forever. But you know, what can you do?
Why is it
Right, we have the microphone.
maybe it's because the Wi-Fi is bad. That would be funny.
Right, so we almost figured it out.
Hmm?
In the meantime, I found you on YouTube.
Yeah. We tried our best. We failed.
That was great. No, I wish that it was great. I was right. Hey, so you had an interview, right?
Mm-hmm.
Where?
All kinds of places.
Like, so much you can.
IBM.
IBM, that's big.
That's
Mm-hmm.
Where did you go?
I worked there for 10 minutes.
What? Okay. You
Okay.
should be doing your presentation.
Nah.
What are you doing?
so
No,
shit.
You worked for IBM for 10 years.
Okay,
And
so
now you're doing so it's your second degree?
masters. Give me a sec. Did I upload it?
I'm resting covering because I in the past many years I've been managing more than actually writing stuff.
Okay.
Yeah. It's a
But,
bit more than I do.
So you're like a lead?
Mhm.
You're a lead manager. That's sick.
if you want to hire
Yeah,
us,
until I got sick of it and I decided to go back to
To suffering? Right?
Yeah.
Code? Right? Okay.
so no, don't take up the word I call it. Fuck. So slideshow.
Hey, let's go.
So wait a second. I mean, I apparently will record it too because I haven't that many.
What did you do then?
many things. I started in a startup that actually was bought by IBM. And then it was a startup in, I don't know if you're familiar, like a virtual storage kind of thing. It was like a while ago.
No
It was
idea.
a big thing.
Yo,
Which-
sorry,
which one?
understood.
Don't worry, we're late.
Got it.
I hate when I start late, but
No, it's good. We're gonna make it close. Yeah.
and I'm not. Yeah, screen capture.
Trying to share it on Zoom?
Yeah,
And
it's a long story.
And we're recording it as well. And we're like 10 minutes late. So we just went there.
Yeah, basically on time. So user setting. here it
Then you have
jumps
more station
down.
than we do already.
Maybe it's because of the virtual camera.
This is Tom. 9. I think it's right. Yeah, it's right. It's good. Now that we've wrote our code, we should submit it. Right, we go to submit section, and we send only the C++ file. That's how usually these sites work. It's testing. Okay. Okay, we got a bunch of time limits. Right, what does it mean, time limits? Well, basically, the testing system, the interface tells me you're an idiot. The program works very slow. Right? Well, it is how to make our we can calculate how to increment it has been on lectures. But basically, it is a very rough estimation of how much operations our program, right? And yes, right? When you calculate something like this, it is always a good idea to look at the have 3 included force. And well, I can prove it strictly. I'm not going to have 40. I'm just going to tell you that I realize it is all of n in the third. This is look at our n limitation. It is like 10 to the power of 5, to the power of 3, which is 10 to the power of 15. You're with us, and that's what matters. Right? I respect that. Okay. Basically, in the competitive programming is 100 million operations. Right. So 10 to the power of 8 is 1 second. Yeah, exactly. 1 second. Our program is going to run for like how many? 10 to the power of 7 seconds. It's like, what, 10 million seconds? It's a lot of seconds. Let's find a way to make it. Yes. Version, it's idea can work, but in general, version just there's like the leftmost element of the subarray, and this is the rightmost, and then we calculate the sum over and over again. We can do this. And it's still going to be valid. And we are not. Right, let's try to explain it. I will try to explain it. Right. Let's look. Like, do you see my cursor? How our force work? We start from first element, and then our right goes from 0. So it's like bim, 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 like this. Right. Then our left becomes 1, and we ignore the first one, and we just go here. Boom, 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 boom. Right. So if we know the sum for this subarray, right, it's very easy to count the sum for this subarray. We just add minus 5. Right? It's fine. Yeah, so we don't erase our sum when we go from one subarray to another. We keep it and we add the last one to it. Right? So that's definitely going to work faster. What does it do? What's the time? It sounded like an insult and it wasn't. Sorry. Yeah. It's obvious that she's actually very smart. We know it. Everyone. Okay, and square, right? I think it's gonna work. We already know it's not gonna work, right? Turn it to here, and it's gonna be 10 here, and it's gonna work for 1,000 seconds, which is much better than what we did. But it wants to. So there's actually a way of this in just one. You can solve this problem with only one loop. That's the idea. That's what I change our world. That's why I like you have time until I finish writing. Sorry. You gotta learn the pressure of competitive programming. Like, yeah, because the competitions have like 4 hours to solve like problems, and it's like one can you talk? Again, I'm sorry I call you, but it's small. You have more time. There's nothing now. We welcome.
Because it's contiguous elements, it's hard.
I'm gonna unmute you. You should pay attention to the prefix. What's a prefix? It's just the first A elements of the first 3. It's all prefix. Right? Let's get rid of an array. Right? Let's count the sum for every prefix. So for this one it's 1, for For this, it's 3 minus 6 minus 3 plus 3 is 0 plus 5 is 5. We count the sum of brackets, right? So it's 1 plus 2 minus 6. The sum of the first three elements. Imagine you are a form that goes to these numbers. There are the sums of brackets.
If you go from 1 to 3, it's only prefixes.
I mean, different prefixes. Close, right? Let's just think, like, what was our initial when we did the course? We checked every single summary, but most of them were equal. They're not going to give us our answer. Why? Because they can be, well, for example, let's take what? This subarray, first 4 elements. Can this subarray, in theory, give us our answer? Give us our maximum sum?
No, because it's 0.
Sum is 0, yes. But, like, how do we know that it's not the answer?
That's the bigger one.
Why do we know this?
Prefix is bigger.
There's a prefix that's less than 0. It's not. Well, that's not just that. You see, if we have a prefix that's negative, we can just throw it out. Right? We throw it out and our sum increases from minus 3 to 0. Right? So if we have a negative prefix, let's always throw it out. Right? So instead of 0, we would get 3. Just this summary. Just the word. It's summary as well. So the actual algorithm is actually we have our sum. We go through every element of the array. Let's go with I. And we do this. We are on element I right now. Our current sum, our current prefix, would be sum plus array of I. Right now, sum is basically a prefix for first I minus 1. But before this, if we had a prefix of negative sum, we just set it 0. Right. We track our subarray from the first element, and we go to the second one. Prefix is 3. We all do it. Go to the third one. Prefix is minus 3. We are not happy. We say, no, we're not going to go from the first element. Our subarray will start from the fourth element because this prefix is negative. So we start from the fourth element and we keep going. Okay, so we always throw away the negative prefix. Okay, I feel like you guys have questions. You want to ask them.
I feel like it makes sense that you put it to 0 if there's a
There's negative.
if there are elements in the array, but
This subarray sum is always bigger than this one. Because how do we calculate it? We take we take 0 and we minus 3 when we throw away the first 3 elements. So when we subtract the next number, our sum always minus.
what I
think about it for a sec to understand it. Maybe I'm lying to you, by the way. Let's try and submit it. Let's try to run it first. Yeah. Another thing is about right in here. You can have like a gut feeling, just maybe you write it, submit it, and then of course you write. You don't actually have to prove it.
In competitive programming, in competition, you have to have like a feeling that it works, and then they just test.
Yeah, you have the system online. So if it didn't work, you know it. Actually, some of them not telling you anything. All wrong answers, by the way. Oh yeah. You're right. You see, we didn't have an answer. So our answer would be maximum of current answer and our sum. Right, let's try this one.
You are being tested all along.
Yeah, but I didn't just make a mistake. I didn't do that. Oh yeah.
Because you're. So can you try for me just to put all negative?
You can see this in the if iteration of the cycle. We are basically searching for the maximum array that ends in the if element. Right. Do this -1, -2, -3, -4, -5. -1. Yeah, maximum. Okay.
Okay, got it.
Right. That was tough. You guys. Let's talk real quick about. We have like 35 minutes. So, alright, let's look at the presentation. Vectors in C++. Oh, thank you. So we know how to write. We know what an array is. We know that if we don't initially know the size of this array, we have to allocate memory. Right? It's using all kinds of things. It's somehow we don't want to do this. We can just do vector. Basically, vector is an array that allows you to add an element to its end, and it will increase its size automatically. Right? And the index is like an array in every sense. You can access an element, find the index, you can get size. That's pretty much it. Right? Let's use some code and that's what happens. Add an element to the end of the vector. This array. Now I have this array. That's all. And the size is going to increase by 1. By the way, this is vector. Hey, that's good name vector. Okay, graphs. Someone what is a graph? It's basically some lines and some dots connected by dots. That's all it is. But like, we want people to think that we're smart, right? So we're gonna give them incredibly complicated and totally unnecessary names. The dot is going to be called a vertex, and the line is going to be called an edge. Right? 1, we store 2, 3, and 4. 2, 3, and 4, all its neighbors. And this way 5. It's called adjacency. Hope I said it's correct. I don't know how to do it. Right, that's pretty much it. Let's solve another. Not all this. Sometimes. We have a graph like this. This graph thing is it's not connected. So if we take it's not connected. It's divided into 2 components. Right. This is component 1, and this is component 2. In what components? If we take 2 vertices from different components, there is no way. The way is basically like we can traverse using edges. There's no way between them. There's no way between vertex 1 and vertex 2. Because they're anything. That's pretty much it. Yeah. Way. Let's call it. Right, but the whole thing is graph. It's not a graph, it's one graph. Okay? Some problem on the graph. That's exciting. It might be our homework soon because Marina already touched it on the lecture.
Yeah.
I lost file there. There it is. Okay, building roads. Wetland city is basically a graph. Every city is a vertex, every road is an edge. We need to add some roads so that there's a road or a path between any 2 vertices. Right? We need to find the minimum amount of roads we need to add. Right? So we have some kind of graph that adds the minimum amount of edges so that the graph has only one road. Right? For this graph, what's the answer? No, we're adding edges. Right? Okay, right now it's 2 components, right? We need to make it so that between every 2 vertices, what does it mean? That means that the component is only 1, right? Because right now, like 5 and 3, they don't have a path. We don't like that. So, what's the answer for it? Right. So, nice. That's a nice observation. If we add at least one edge, these 2 components become 1, right? Great. Now there's a path. We're happy. Right? How do we use this idea to solve this? You get the components. Yeah. Yeah, we can. Don't think about the way it's written in the code. We're gonna do this like this. Right, yeah. Right. Any components, we can use n-1 edge to connect them all. But it's pretty much just pretty easy. We have we want to connect all the balls. We need like 1 stick, 2 stick, 3 stick. That's enough. So we have 4 balls. We need 3 sticks. We have n components. Let's look at them. We have k components. A minus 1h. Let's look at the algorithm. The question now is how do we count pretty much yes. We do, but they don't usually. So we have what's our input? Our input is nm, right? nm. Okay. N is the amount of vertices. M is the amount of edges. And then we are given m edges. We're just given pairs of vertices which define an edge. Every edge is connecting to vertices.
So you don't get the adjacency list, you just get the pairs of.
Yeah, but we can do it ourselves, right?
Yeah.
And then, start the list. Let's go back to presentation. For every vertex, we need an array which stores all its neighbors. There's many ways to do this, but the most comfortable one is to use vectors. Remember those? Dancing guy, right? MXN again. Might need to change it. Yeah, 10 to the power 5. Okay. What the hell is this? It's basically an array of vectors. Basically an array of arrays. It's like a matrix, right? But for every element, the size of the array is 0 for now on the declaration, right? So it's an array of empty vectors. That's all there is. Now we're given an edge right in here. What do we store it in our adjacent space? Well, we say that vertex A has a neighbor B. You understand this line? Why did I write this?
Every vector has a number, and you can just.
What am I saying about vector? Like a door in the back?
No, vector.
Vector. Oh, yeah. Yeah.
So every one of them can be addressed in the graph. So you can just go by the index based on the vector, backdoor, whatever you want to call it.
Right. So yeah, pretty much. So in the vector under the index of A, all the neighbors of A, right? And we just add B to this vector. We have a two-directional graph, right? So B has a neighbor A as well. a way to traverse it, right? Let's everybody. It's called DFS, Deep First Search, like in the binary tree. We are given our vertex, which is, that's pretty much it, right? What do we want to do from our vertex? Like, we want to call our function recursively from every neighbor of one. This we go through every neighbor of u, and we say, let's call our function recursively from this neighbor. What's the problem? Recursion is better. Go through all the vertices components. So if I start from one, I want my recursion to visit all these vertices in this component. Two is a neighbor of 1, and then we go from 2 to 1, because 1 is a neighbor of 2, right? So it's just, we don't want that. So how do we solve this problem? How do we not get the same vertex twice?
You use remember what you already traversed by using it as a variable into the function.
You mean like to give a function previous, the one we came from. Yeah, you are looking at right now like a good programmer. We are not. We don't need to give a function anything. We can just make it global variable. Right. Let's make an array S, which is visited, which is by default all zeros. None of them. The vertex, we say that visited of u. And here we need an if we already visited I, we should continue. We shouldn't move cursor from this neighbor. Right? He's angry because it's recursion. But yeah. But yeah, that's pretty much it. Right? We go through every vertex and we mark it, which is important. Right? So how do we traverse the whole grid? How do we visit everything?
You can do something already
from just the first vertex, right? What it's gonna do, it's gonna visit it to all of the vertices of the first compound, right? And then we can go through every vertex we've got and say it wasn't visited already. It's in a different compound, right? So we need to visit it as well. And is this going to work? Is this enough? Let's solve the problem. All the vertices in the graph. Yeah, right. So you don't even need actually the first DFS call, right? So what is it going to do? It's going to go from every vertex from 0 to vertex. And if it finds a vertex that wasn't visited yet, it calls DFS from this vertex. It marks visited all the vertices in its compound. Component. Right? So 1, 2, 3 are going to get marked as visited. In our form, when we get to the second vertex, we are not going to call DFS from here because not visited is going to be 0. If it's not we're not going to visit 3 as well. But when we get to 4, we will not visit it. Well, the new compound, we will get this from this vertex and visit all its compound. So like it's a lot of scary words. Ask me a question.
Every time you compound, you mark every compound.
Yes. Right, we're going to solve this later. Right now, just so any questions?
Like 1, 2, 3 separately, and then like in a separate.
You're right. We're trying to figure out how many components we've got. Yeah, let's figure out what it is. How hard is the usual hierarchy? Yeah, like when do we increase it? Right. So every time you stumble across a not visited vertex, it means we found a new compound. We increased compound. And then we can just print it and be happy. Is this enough?
Probably. Seems like it's going to be slow now.
It visits every vertex once.
Yes, but then.
The output carefully because they don't only want the k, the number of required rows, they also want the rows itself. Right? So they want to print what kind of edges we want to create. This.
So we have to mark the places that we have in the component and then see how we connect them.
Right. That's pretty much it, right? So every time we find a new component, we know that I. Right. So if we connect this line to the previous line that was found, not visible, then we can just like bad. It's recording. You're recording too, so. Right, what was this? Okay. When the variables for the last compound found, right? Some vertex from the last compound, basically. How do we why? Because you have to connect last. But you don't need all the previous ones. You need only one for the last one. Yeah.
Vertex is like the
We can print it. We have to store it because we don't know the compound, the K yet, right? The amount, and we need to print it first. So yeah, let's create some kind of structure that's going to store our edges. Array. Another way to write an array is it's just a paragraph. Okay, and it's vector as well, so it's like by the definition. Okay, so I don't know how to call this paragraph. I'm having a crisis.
vertex, whatever.
Let's call it Bob. I always like the name Bob. I don't know why. Bob is I don't care about this one. Yes, if you give it as a homework, yeah, I'm going to be very angry. But it works fast, and we write it in very short time. That's good. Okay, Bob is minus 1. Why is it minus 1? Because no other vertex is minus 1. We know that it is not good. So what do? We found a new compound. If Bob is not minus 1, right? So we have a previous compound. Then he doesn't like Bob either. Right, it's fine, okay. We need to add our age to the answer.
What does this mean? If you found a compound before, you want to add this compound, you mean?
So for the first compound, I don't add anything. This one. When we find the second one, we will connect it with the previous one. Yeah, let's wait. Yes, I will. So if we have a previous compound, if Bob is not minus 1, then we add an edge. And then we change our Bob to I, because it becomes our new previous vertex, our new previous compound.
You don't really need to do it, but yeah.
To do what?
Call this Bob. No. I mean, if you set Bob to one vertex, whatever it is, like if Bob is like one, then you set two vertex and every other, then you can put it to that vertex, that works. But
I feel like it.
if you set it to minus 1, and then find the first compound, and you set that vertex, every other compound to that vertex, but it doesn't matter.
You're right. Yeah, you're right. Let's do it this way. Right, Bob is our previous compound. We increase the number of compounds, and we call DFS to mark visited all the vertices of these compounds. Of this compound. Right. So end line is just backslash n. Okay. represents. Right? That's all there is. Now, this code is not. It's not the idea. But the way we wrote it, we missed something. We missed code. I don't know if you guys can catch it. So it has something to do with indexes. We mark vertices from 0 to n minus 1 because it's comfortable to work with the arrays, right? Arrays have indexes from 0 to n minus 1, so we do this. But when we read it, we read indexes from 1 to n. You see, like this. AB from 1 to n. So we actually need to decrease it by 1. It's a very common mistake. And now we're good. But let's try to run it. Maybe it's not going to work. I don't know.
The adventure is what matters.
True. Especially when it's like 200 lines of code and you have 5 minutes before Olympiad ends.
Yeah.
You don't get more fun than that. What's going on? It's compiling. We gotta give it some time. Right. Let's run it. 202. 02, something's off, right? So first of all, we printed more edges than we need. We need 1 edge, and we printed 2. And second of all, we printed it in a 0 to n minus 1 in the indexes, right? So here we need to plus 1. Do you understand why? Everybody? No?
Where?
In here.
So basically, vertices start from 1 to whatever number, and we are counting them from 0.
Yeah, pretty much. So during our programs, all the vertices are from 0 to n minus 1, but our testing system wants it from 1 to n, right? And why is compound is 2 when it should be 1? Why?
Compound, it's 2 when it should be 1.
Mm-hmm. Now, what the hell is compound? What is this variable? What do we count in it?
We're counting different sets of nodes that are connected between each other.
Different compounds.
Yeah.
But that's not what we need to print. We need to print the number of edges. You remember the idea in the beginning? Yeah, it's number of compounds minus 1. So we just forgot to subtract 1. Okay, let's try this. Dude, I swear to God, like 5 years to compile a program, it's wild. Okay, 1, 1, 3.
It's not the same that they gave you, but I think it's still right.
And imagine it in our head. We have 4 vertices, we have 2 edges, right? 1 and 2 are connected, 3 and 4 are connected. It's like this, 2 lines. Connecting 1 to 3. Vertex from 1 line to a vertex from another line. Let's try to submit. Hey! Dude, I love green.
The compiler complained anyway, but
Oh, he always does. Yeah.
yeah. After just a couple of violations of the Geneva Convention,
Yeah.
it works.
Okay. Right. So that's the first one. The first was an example. Problem where we come up with an idea, right? It's the first technique diagram. So if you go to the next diagram, we can go more like more problems that were given here. Like this one is a real competition. Yeah, 100%. That has nothing to do with subject.
To add a actual programming part to the club because a lot of people that are doing mostly the first degree do the minimum and then they go out to the world and want to get hired and it's like, okay, but can you like program something in like actual time constraints and like whatever and like no, I never did in university because it's not a requirement. In this case, like you have the opportunity to do actual programming. The question you will be asking here because like this is
You're gonna like you're gonna do every day for the rest of your life. You're working from right, searching box, understanding why it's working too long, or if we use too much memory, if we use the manuals of the crash. So basically the demo of what you are gonna do next. Yeah.
Yeah. Or an accountant.
I have another problem, but we have 3 minutes. So I'm probably it starts to slow. Anyway. Only C++.
You're not using C++, you will not get far.
But I mean, you could write it in Rust, but it would take too much
Yeah,
time.
that was
Rust. Yeah, if you write it in like Python or Java, even if your idea is correct,
Yeah.
it's still not gonna come through the limitations. Yeah.
And your time is limited for every exercise, right?
What do you mean why?
I mean,
right.
Right. Now, he said like everything is limited, so the
Right,
time
yeah,
to write
yeah,
is
yeah,
limited,
right.
the time to run is
And
limited.
it is all usually said in the task, right? Like here it is 1 second, and memory is given too, but usually they don't like.
And
The idea is to cut the time, not the memory.
And also, I don't know if you ever participated in an Olympiad, I did math, like in high school, but basically they give you an amount of time to do all the problems and you are supposed to divide the time by yourself. And if you do like 1 hour and 50 minutes for the first 4 problems and you have 10 minutes for the last one, good luck, like you're not doing it. You have to divide the time by yourself, or how much time you allocate to every problem.
Yeah, it's like any other competition, pretty much. Math, yeah.
Yeah.
There are actual online competitions, like on Code4Sys, for example. It's like every week there's a round, different categories, different difficulties. So if you guys know nothing, you can still participate and find something interesting, right? So check it out.
Yeah, it's the same as cybersecurity competitions that are like once a week. The problem with the competitions for cybersecurity is they are on the weekend, and that's why we're trying to make our own. But like for Code4Sys and like there's the weekly lead code and whatever, we're probably going to send like a weekly challenge on the group. So like every
Like
week.
one problem every week. Yeah,
Yeah,
it's
every
really good
week.
to have homework and stuff. Yeah.
I mean, yeah,
It's
not more than one, but yeah. For whoever's watching, I hope you enjoyed. I hope that Artyom didn't commit too many crimes against humanity in this one,
Right.
but we're going. Next
Coming
week,
in, there's gonna be way more crimes next time. Okay.
and hopefully next week we're going to do the first web-based cybersecurity one. I just have to find the time, like when's best, because like right now not a lot of people will come. So I'll stop the recording and I'll try to edit it. So thanks everyone. We had so many problems today from this class, so bad.